This is RC. This is RE. So the example here is beta is 100, VBE is 0.7 volts at IC equals to 1 milliamp. So design the circuit. You know, when I'm talking about design the circuit means, you know, just design the resistors. You cannot change too much of the transistor itself. You cannot just directly cut it and change the parameters inside the NPN junction, right? The only thing you can modify are the resistors. And the voltages are already given. You cannot change the power supply. So design the circuit means design the value of the resistor you can plug into the circuit to make it be operated at a certain condition. So design the circuit so that IC is 2 milliamps and VC is plus 5 volts. So VC means the voltage here, 5 volts. So this is given whenever it's being operated at that voltage for VBE and that current for IC. When VBE is this, IC is this, right? So design a circuit so that when IC is this, VC is this. Looks different, right? So when VBE is this, IC is this, but here is different, like IC and VC. So disregard the difference between these two statements. Can we just make it happen? I mean, this is given, and this is asking for. So we need to design RE and RC to make this happen. And that's it. So what are these equations you have learned? I mean, just by looking at this one, IC, you are thinking that, hey, when IC here is, we don't know RC and RE yet. You're being asked to design it, right? So we don't know these two resistors. And IC, when IC is 2 milliamps, and VC becomes 5 volts. So what is this telling you? You don't have to care about these ones here yet. And now we can directly calculate for RC. Is that correct? So what is RC? So here's the final result, right? Whenever VC here is 5 volts, I need IC to be 2 milliamps. All right? You don't even need to care about anything here. Just by doing this little calculation, you can get RC. Can you? Ohm's law, right? RC equals to 15 volts minus 5 volts over IC, which is 10 volts over 2 milliamps, which is 5. So 5K. So now we know that RC has to be 5K ohms. And now you are looking at the bottom because you want to get RE, then you are done. Design the circuit, just design the resistance, value of the resistors, so you can find out the resistors in the drawers in the lab and plug into the circuit, you're done, right? So now you're thinking, hey, that's NPN junction, the PN junction here, so it's 0.7 volts, and I know here's 0 volts, and it's a voltage drop, which is 0.7 volts, so here is negative 0.7 volts, so I got a voltage drop from here to here, so I can get IRE equals to negative 0.7 volts minus negative 15 volts over IE. Since I know IC already, I can easily find IE because IE is 1 over alpha IC. You still remember this? Okay, if you don't, you remember it now. I mean, I'm just repeating myself. Repeat. Keep in mind. Is that correct? You're like, just spent 5 minutes and you're asking if this is correct. Where is the problem? Where? I'm making that mistake now, so you are not going to make the same mistake in the future, since I'm showing you that which is the common mistake you are going to make. What's the problem? How can I assume the voltage here is 0.7 volts? Whenever VB is 0.7 volts, IC is this, right? Remember, IC equals to IS times E VBE over VT. When you have a different IC, now IC is different, it's not 1 milliamp anymore. You cannot assume VB is 0.7 volts, you have to calculate for VB first. So that's why you cannot start from here. So all the calculations here are wrong. But the equations are still correct. But the values are wrong, right? So how can you get started? Where can you get started for this calculation? Now we know IC, right? Since we don't know VBE, we want to know RE. Do we know IE? Can we get IE now? Yes. Here's IC. What is alpha? Yeah, good job. What is beta? Can I remember it now? If not, please do it. Remember it now, okay? That's critical because you have to know this in order to find out the direction for the calculation, okay? Do we know IE? Yes, we know. Do we know, no, so we know IE, do we know RE? No, we don't, right? So do we know the voltage here? Yes. Do we know the voltage here? No. How can we get the voltage here? You are thinking, hey, we know the voltage here is 15 volts, and we know here is 5 volts. Do we know the voltage here? If we know VCE, then 5 volts minus VCE, we can directly get the voltage here. Do we know VCE? No, we don't. So that's not the way to calculate for this voltage out here. Do we know VBE? Can we calculate for VBE? So the voltage here is 0 volts. If we get the voltage difference between here to here, so we can definitely find the voltage here at this point. Okay? So we want to calculate for VBE. How do we calculate for VBE? Remember? If this is IC1, IS is a constant. All right, cancel, cancel. What is IC1? 1 milliamp. What is IC2? 2 milliamp. What is IC3? E. Do you know VBE1? Yeah. So can I calculate for VBE? Yes. We got a VBE here. So what is VBE? The voltage between B and E, right? Do you know VB? Do you know VB? What's VB? 0. What's VE? Vitamin E. What's VE? Negative. So VB is 0, right? VE is, we don't know. And VBE is calculated here already. You can calculate it. Equals to 0 minus, so VB minus VE. This is already calculated. You can find out VE equals to what, right? So VE can be calculated. So you got voltage here. What's next? You got a voltage here, you know the voltage here, you just do a Ohm's law, right? Voltage minus voltage divided by IE. Do you know IE? Yes. So you can find RE. I'll calculate it. RE equals to VE minus negative 15 volts over IE, right? IE is 1 over alpha IC. For the problem, I won't calculate it, but you know how to do it, right? So I'm gonna scan the notes and post it to the website, so find out when you are doing the homework assignment if you need it. Another thing you need to know, important, BJT load line and Q point, quiescent point, or Q point. So what is a load line here? If I draw a little circuit, VCC, right? Collector, VCC, RB, RC is 10k ohms, and IC is a current flows into the collector, IB is the current flows into the base, and it's directly grounded, and the voltage difference between the collector and emitter is VCE. Okay? So if IC is 0, for example, at some point, IC is 0, what is VCE? If IC is 0, what is VCE? VCC, right? 20 volts. If VCE is 0 at some point, what is IC? If VCE is 0, all the VCC will be dropped across RC, and you can find out IC is directly VCC over RC, 2 milliamps. If the x-axis is VCE, the y-axis is IC. So when IC is 0, on the y direction, IC is 0, VCE becomes 20 volts. When VCE is 0, IC is 2 milliamps. So RC is a load. Not because of this, okay? RC is a load because this is a transistor. And remember, you can plug in a motor here, you can plug in LED here, you can plug in whatever you want to plug into here, right? And so you can use a little current and being amplified, and you can drive it, okay? That's a little amplifier. So RC is a load. And because of this, and we can, so RC equals to what here for this equation? Where's the equation in this circuit? This VCC minus IC times RC equals to VCE. Is that correct? For this circuit, VCC minus VCE or minus IC RC is VCE, right? So what are the variables? That's a load, it's a constant, right? It's not changing right now. So in this coordinate, so IC and VC are changing. And is it linear? Yes, there's no square, there's no other functions. So if I already have these 2 points for these 2 examples, what you think about the function, the line? Okay, so that's the load line. So you'll see some of the problem in the homework assignment asking to draw the load line. You know how to calculate it right now? You have something like this. You just find out when IC is 0, what is VCE? When VCE is 0, what is IC? Then you have 2 points. You can form a line. Just draw it, right? Done. That's a load line. Load line. And because VC and IC for this transistor, it looks like, so the operation, whenever it's being operated, the IV curves of this BJT looks like this, right? Like this. So all these points are being called as Q points because they can be, this transistor can be biased at any of these points, any one of these points, sorry. Does that make sense? It doesn't have to be operated over here, right? It's gonna cut off that transistor. So it's being operated at any points in the middle. So all these points are called Q points. How many IV curves do I have? Infinite. I just drew like 4 or 5, but there are many. Infinite number of lines, right? You can operate it at 15 volts, 15.1 volts, 15.1111, a million ones volts. So you get infinite number of lines, right? But any point here, any point can be called as a Q point. But you can choose a better Q point because it's going to affect the swing, the input swing of the amplifier. How that works? Let's take a look at it really quick. So for example, for the same example, right? Same example. I'm going to draw this IV curve one more time over here. That's an extreme case. That's a cutoff case. So this here is 2 milliamps. It's called IC set. Keep in mind, if you see this term on the homework assignment, you want to know that this is IC set. Because here's a linear region, here's the saturation region. It's already saturated. So ideally, IC set should be the 2 milliamps. But you know it won't be, so this curve, this IV curve, won't directly overlap with the y-axis, right? So there will be a little gap. But ideally, let's just treat that IC to be 2 milliamps. That's the IC set, ideally, okay? And these different curves here are different what? So why these curves are different height? What makes them different? VC, phase current. So these are the different IBs. So for example, the first one here is IB is 10 milliamps, microamps, and here's IB is 20 microamps, and this is IB equals to 40 microamps, and here's 20 volts. 20 volts. So the middle one will be the Q point you want to choose. Why? There are many Q points, right? Many Q points. I don't choose this one. So the reason for that is this can be confusing, but now let's try to understand it. Okay, let me explain it. So the curve has been drawn like this, which means the I's and V's are going to follow these curves. Is that correct? It's not going to swing in a different pattern. It's going to swing in that pattern, right? It's going to change in that pattern. That's why we get a curve. And if the Q point is being chosen at this point, which is 10 volts, so ideally, the VCE can swing symmetrically like this. What's the point to have a circuit like that? It's not just directly, yes, you can use it to drive a motor, but what about the AC signal? It's a little alternative signal from the sensor, so you want to amplify it. We want to amplify it, so there's a rail-to-rail voltage. For example, here's a power supply. That's a top rail, that's a bottom rail. All right, usually you want to set up the DC off side in the middle so you can get the symmetric swing of the signal. Why? Why you want to make that? Why you want this to be symmetric? Because the signal is from the analog world, it can swing upwards or downwards randomly at the same level. So you want the top range here to be the same as the bottom range. So whenever the signal is swing at the same amplitude on the two sides, you can still amplify it without distort it, without clip it. So now if you have a symmetric swing range like this for VCE, and now you can tell that here's the IC. Ideally, that's the full range of the IC. And the IC can swing symmetrically as well, like this. If you choose the Q point to be in the middle, all right? So how IB is going to swing? Where are the IBs? I mean, X and Y, so it seems like this two-dimension plot doesn't have any dimension for IB to fit in there, right? Because, so where's IB? That's a curve it has to follow. No other choices. So how IB, so these are the IBs, right? When IB changes, it has to follow this line. Can this line make an IB change? No, so along this line, is IB changing or not? Yes, see, IB it's changing. IB is the input, B is the base. You have a DC voltage here, you bias it whenever, why it's called Q point, quiescent, right? Whenever there's no alternative signal to bother it, right? Just like sitting there. Superposition, is helpful, right? How is that help to understand this? Superposition. When you're only looking at the DC signal, you ground the AC signal, so you have a DC voltage over there, right? If you only look at AC signal, you're going to ground the DC signal, but only add that AC signal to the output, to the result. So eventually you have these two parts, and you add them together. So you have a DC offside from the first power source and AC swing being added to it. That's the idea of superposition. Helpful. Okay, so same concept can be applied to here. The transistor has to be biased at a certain Q point. So it's sitting there like the DC offside of the amplifiers. So whenever I get a signal, it's going to swing around that DC offside. Okay. So IBs, usually they are small, but here is a large swing. It's going to reach the top rail and bottom rail. So how IB is going to swing whenever these are swing like this, how IB swings. I mean, how that works? keep in mind, there's nothing here. There's no dimension here. That's a sine wave. I draw it like this just for you guys to look at it, but actually just one line swing back and forth. Does that make sense? There's no time dimension here. There might be, but it's gonna be nothing different from like a point swing back and forth. Okay, so you're gonna swing back and forth along this line and making different IBs. How? All these IBs are different. I mean, so there are infinite number of IB curves. Whenever it moves back and forth, it's changing IBs, right? Not linearly, but it's changing IBs. Not like from here to here, it's 20 microamps to here, it follows this line. This is 20.1 microamps, right? So what about the next line? Like 20.2, 20.3, doesn't matter. I mean, it's just translating that IB into IC and VC swing. So all the input are from IB because that's the base input. So all the signals are going to come into the base, all right? And then make that happen, make all the gains, see the gains. So why we want the Q point in the middle? If it's not in the middle, what's going to happen? Let's look at one curves. It's not in the middle, then what's happening? It's called IC what? What about this? A VC max or something? I forgot. Just VC max. So if I choose this as a Q point, that's a swing range. Why? You just want to make the amplitude to be this as a maximum, because if you have a larger amplitude, then what's going to happen is here you got a lot of space to swing, but here not. If you have a sine wave, you are going to see the bottom sine waves being clipped. All right. Same for the IC. Whenever the Q point is over here, what's going to happen is it is trying to swing like that, but actually cannot because there's no power supply at the bottom to give that capacity. Make sense? Okay. So ideally, whenever you are trying to find out the Q point, should you use half of VCE max or half of IC set max? IC set. Which one to use? Where you want to start with? Same. Why? Yeah, it's linear. It's VCC minus, remember if you look at here, the equation, VCC minus ICRC equals to VCE. Okay? If you use half IC, you are going to get a half VCE. The same, if you use half VCE, you are getting a half IC. So it doesn't matter where you want to start with. You pick up, if you find out the IC set, you divide it by 2, you find the Q point for the current. Then if you just plug into here, you can get the Q point for the VCE, vice versa. If you find the VCE first, you divide it by 2, and then plug in here, you can get the IC Q point, ICQ. It's the same, it's also a half of IC set. All right, so seems like we cannot finish everything like I expected. So you won't be ready to do all the home assignments today. So I will make the deadline to Monday after next week. So we'll finish off everything on Monday. All right, let's look at one example here. Oh, one more thing. So effect of the emitter resistor. So these ones do not have an emitter resistor, because the emitter is directly grounded. All right. So what if the circuit looks like this? Oh, sorry. There's still VCE. Is it going to affect your calculation for the load line? Not too much. So the equation just becomes VCC minus VCE equals to IERE. Very similar. If you compare when you put the load, connect the load to the collector, I mean, pretty much the same, right? So no difference. So this time here, RE is a load. How do I know that? That's the only thing has a resistance. Hey, the wire is a load. I just want to drive the wire. Looks cool. I want to heat it up. So that's the only load you have. What about this? I got two. I got both resistors. Both of the terminals have resistors. So in this case, usually we assume IE is the same as IC because IB is tiny and usually the beta is 100 or 200, right? So IE equals to what? IC? IC equals to what? IE? Let's just repeat ourselves, right? Repeat, repeat, repeat. IE is what? IC? Huh? Half? No, no. So IB, IC merged to get IE, right? And IB is tiny because IC is IB being amplified by 100 times to get IC. So that's why IB compared to IC is tiny, a little bit, only 1%. So that's why we can assume this because IE literally is IC plus IB, and IB is tiny, right? That's why we can assume this, right? But now here, so IE is literally what I see, right? Right? So what is alpha? What is beta? Okay. So in this case, you have resistors both on the elector and also the emitter, and we can assume this. Then what's going to happen is VCE. Why we want to start with VCE? Because that's the IV curve. VCE is the x-axis. We're going to just get a curve. So VCE equals to VCC minus IC, since we can assume IC equals to IE. It's the same current as the mainstream current. Here is just a little stream. Here is huge, right? Huge. So VCC minus IC times what? That's easy. Let's just wait until 10, 12, 10, then we're ready for lunch. I still have a lot of examples to come. Forget about it. No rush. So what is this? Right? So the big stream is IC, right? Because IC equals to IE. Right? Here's VCE. So you have three voltage drops. RC is one, VC is another one, and RE is another one. So the total voltage drop minus IC times the two resistors. Okay. More exciting examples will be covered on Monday. So the deadline for homework 7 will be Monday after next week. After next week, not next week. Okay. See you next week.